Imagine a high-traffic fintech platform in 2026 experiencing a micro-network fluctuation. In an instant, a network partition severs the connection between your primary database nodes. Node A and Node B both lose contact, and through a series of faulty heartbeat timeouts, they both conclude the other has failed. Both nodes promote themselves to leader status. This is the split-brain scenario, catastrophic state, where two autonomous nodes begin accepting conflicting write operations for the same ledger entry. As user X deposits funds in Node A and user Y withdraws from Node B, the distributed state diverges irrecoverably. By the time the network heals, you are left with corrupted data, financial discrepancies, and a system that can no longer guarantee the source of truth. This isn't just a glitch. It is a fundamental failure of coordination. By the end of this lecture series, you will master the exact protocols and architectural patterns required to ensure this disaster never strikes your production environment. To survive the chaos of distributed systems, an engineer must move beyond hope-based development and embrace architectural resilience. In this session, we are going to establish a diagnostic framework for distributed consistency. We will analyze how to detect partitions before they corrupt state, and how to implement quorum-based voting to ensure only one leader can ever exist. We will look at real-world failures where last right wins strategies led to millions in losses, and contrast them with robust consensus models. Whether you are building microservices on Kubernetes or designing a global edge network, your ability to diagnose and prevent these failures is what separates a senior architect from a junior developer. We will bridge the gap between abstract theory and the hard-coded reality of distributed logs. But how can we prove this disaster is mathematically inevitable in any distributed environment? Let's look at the survival guide and the theoretical limits you'll master by the end of the session. In the world of distributed engineering, the CAP theorem is our gravity and inescapable physical law. It dictates that in the presence of a network partition, you must choose between consistency and availability. You cannot have both. In modern 2026 microservice architectures, where network partitions are a statistical certainty rather than a rarity, we almost always operate in partition tolerance. This forces a brutal architectural decision. Do you stop the system to maintain data perfection, or do you keep serving users at the risk of returning stale data? As we move toward global edge computing, the latency overhead of maintaining consistency becomes a massive performance bottleneck. Understanding this trade-off is the first step toward moving beyond simple CRU to apps and into the realm of high-scale system design. Is CAP the final word on distributed design? A surprising counter-argument exists that suggests we've been looking at the triangle all wrong. Modern architecture has evolved past the binary simplicity of CAP into the Paxos theorem. Consistency isn't just on or off, it is a spectrum of trade-offs between latency and correctness. Linearizability, or strong consistency, provides the illusion of a single atomic data store, but it comes with a heavy latency tax because every node must agree before a response is sent. On the other end, eventual consistency offers lightning-fast performance by allowing nodes to converge over time, which is acceptable for social media likes but dangerous for inventory management. In the middle, we have causal consistency and read your write its consistency. As an IT strategy consultant, I often see teams waste millions by choosing strong consistency for data that doesn't require it, or vice versa. We must map our technical choices to business value. We know the theoretical limits now, but why did the industry's first attempt to solve this, the legendary two-phase commit, fail so spectacularly in the cloud era? Historically, we relied on the two-phase commit, 2PC, protocol to manage distributed state. It worked by having a coordinator ask every participant to prepare and then commit in two synchronous steps. However, in the age of massive scale and unreliable cloud networks, 2PC became a stop-the-world bottleneck. If the coordinator or just one participant node hangs, the entire system blocks, holding locks on precious resources. This lack of fault tolerance led to the development of modern distributed consensus. We transitioned from rigid synchronous locks to the resilient world of replicated state machines. From the academic origins of Paxos to the pragmatic design of Raft, the industry shifted toward protocols that can survive node failures without stopping the world. The era of 2PC is dead for global scale, but its successor, the consensus protocol, brought a new war, the battle between the complexity of Paxos and the clarity of Raft, which we will deconstruct in the next chapter. To understand distributed systems, we must start with Paxos, the foundation of modern consensus. Developed by Leslie Lamport, Paxos is the gold standard that won a Turing Award. In the professional field, we often say there is only one consensus protocol, and that is Paxos. Everything else is just a variation or a broken implementation. However, the original paper describes a synodic council on a Greek island, using complex metaphors that leave many implementation details like leader election as exercises for the reader. This abstraction is both its greatest strength and its most notorious weakness. While mathematically perfect, the gap between the theory of Paxos and a working, production-ready system is a chasm that has swallowed many engineering projects. It remains the most respected, yet feared algorithm in computer science. Question: but how exactly does this mathematical beauty translate into a series of network messages that nodes can actually understand? Paxos operates through a strict hierarchy of roles: proposers, acceptors, and learners. The process begins with a prepare phase where a proposer picks a unique number and asks a majority of acceptors to promise not to accept lower-numbered proposals. This effectively acts as a distributed lock. Once the proposer receives these promises, it moves to the accept phase, sending the actual value. Only when a majority of acceptors confirm they have accepted the value is the agreement finalized. This majority wins or quorum-based approach is what allows the system to survive the failure of individual nodes. However, in high concurrency environments, you might face livelocks where two proposers keep outbiting each other with higher numbers, preventing any value from ever being chosen. This complexity is why implementing multi-Paxos for repeated decisions is a task usually reserved for the world's most elite infrastructure teams. Teaser, if Paxos is this difficult to implement correctly, why do we see it mentioned in every major cloud provider's core white papers? In the real world, few systems run pure Paxos. Instead, we see Paxos-ish implementations. Google's Chubby and the globally distributed Spanner database are the most famous examples, but even their engineers admit that moving from the paper to production required massive efforts to handle disk corruption, master leases, and network partitions. The mathematical model assumes simple failures, but the real world is messy. This implementation gap led the industry to seek a more pragmatic alternative. Developers needed a protocol that provided the same safety guarantees as Paxos, but was designed from the ground up to be understandable and maintainable by human engineers. This shift in focus from theoretical elegance to practical engineering led to a revolution in how we build distributed clusters. Payoff, this search for human-readable consensus led to the birth of a protocol that has now become the industry standard for modern cloud-native tools. Raft was introduced by Diego Ongaro and John Osterhout with a single, clear goal: understandability. Unlike Paxos, which tries to solve consensus as a single abstract problem, Raft decomposes it into three manageable subproblems: leader election, log replication, and safety. By enforcing a strong leader-based model, Raft simplifies the complex state transitions found in decentralized systems. In a Raft cluster, there is only one source of truth at any given time: the leader. This leader is responsible for managing the replicated log and coordinating with followers. It's not just an algorithm, it's a practical framework for building reliable systems that teams can actually debug and audit without a PhD in formal logic. Question: but what happens when that single source of truth, the leader, suddenly disappears from the network? Leader election is the heartbeat of Raft's resilience. Every node starts as a follower. If they don't receive a heartbeat from a leader within a randomized timeout period, they transition to a candidate state and start an election. This randomization is the secret sauce. It prevents multiple nodes from starting elections at the exact same time, which would lead to split votes and paralysis. A candidate becomes a leader by winning a majority of votes for a specific term. Terms act as a logical clock, allowing nodes to detect obsolete leaders. If a leader goes offline, the cluster automatically triggers a new election within milliseconds, ensuring high availability without sacrificing the integrity of the data. Teaser: once the leader is standing, the real work begins, ensuring every node in the cluster sees exactly the same sequence of events. Data consistency in Raft is handled through log replication. When a client sends a command, the leader appends it to its local log and broadcasts append entries requests to all followers. Crucially, the leader does not commit the entry immediately. It waits until a majority of followers have safely stored the log entry. Once this quorum is reached, the entry is considered committed and is applied to the state machine. The leader then notifies the followers of the new commit index in the next heartbeat. This majority wins rule ensures that even if some nodes fail, the committed data survives as long as a quorum is reachable. It is a rigorous process of synchronization that guarantees a total ordering of events across the entire cluster. Payoff: this level of reliability is exactly why the most critical components of modern infrastructure are built on top of Raft. If you look at the modern cloud stack, Raft is everywhere. Kubernetes, the backbone of modern container orchestration, uses etcd to store its entire state, and etcd is fundamentally powered by Raft. HashiCorp's console uses Raft for service discovery and configuration management. Even distributed SQL databases like CockroachDB and TDB utilize Raft for managing their data ranges. These systems choose Raft not because it is mathematically superior to Paxos. In fact, their theoretical guarantees are equivalent, but because the Raft implementation is easier to verify, audit, and extend. When you are building a system that cannot afford to lose a single byte of configuration, the ability to clearly reason about the code is more valuable than theoretical elegance. Raft has democratized consensus for the average infrastructure engineer. Question: so, if Raft is so great, should we just forget that Paxos ever existed? To summarize the consensus Duel, Paxos offers unparalleled theoretical flexibility and is the ancestor of all consensus protocols, making it suitable for massive, custom global-scale systems like Google Spanner. Raft, on the other hand, wins on time to production and maintainability. Raft's leader-centric model is easier to grasp, but can become a bottleneck in massive, write-heavy workloads compared to the more decentralized potential of multi-Paxos. As an IT strategist, your choice depends on the trade-off between implementation risk and specific performance needs. But consensus is only half the battle. Once we have a shared log, how do we efficiently manage the state that grows within it without overloading our databases? bridge. That is why in the next chapter, we will look at how to decouple this state using CQRS and event sourcing to build truly scalable and observable architectures. In traditional architectures, we typically store the current state of an object in a relational database. If a user changes their shipping address, the old value is overwritten and lost forever. This is a massive loss of business intelligence and a nightmare for distributed debugging. Event sourcing changes this paradigm entirely by storing every single state change as an immutable event. Think of it like a bank ledger. You do not just store the final balance, you store every transaction that led to it. This approach provides a mathematically verifiable audit trail and allows us to understand not just what the state is, but how it became that way. By treating the log as the source of truth, we decouple our data from the immediate needs of a specific schema, allowing for much greater flexibility as the system evolves. But how do we turn a long history of events into a usable state without waiting forever? One of the most powerful features of event sourcing is the ability to perform time travel debugging and comprehensive auditing. Because we have every event since the system's inception, we can reconstruct the state of the system at any specific point in history. This is invaluable for regulatory compliance in industries like fintech or healthcare, where knowing who did what and when is a legal requirement. In a distributed environment, this also helps in diagnosing race conditions that occurred yesterday but are no longer visible in the current database state. We simply take an empty object and replay the events sequentially until we reach the desired timestamp. This deterministic nature of event replay ensures that our logic is consistent across different environments, from production to local testing. Is replaying 10 million events every time a user logs in actually feasible for a high-performance application? To maintain high performance as the event log grows, we implement a snapshot strategy. Instead of replaying thousands of events every time, the system periodically saves the materialized state into a separate snapshot table, for example, every 100 events. When the system needs to reconstruct the state, it simply loads the latest snapshot and then only replays the few events that occurred after that snapshot was taken. This reduces the reconstruction time from seconds to milliseconds, making event sourcing viable even for high-traffic systems. This technique is similar to how database redo logs work, or how certain distributed consensus protocols manage their internal state. It is all about balancing the purity of the event stream with the practicalities of latency and throughput. With performance solved, let's look at how this changes the game for distributed locking and data consistency. Event sourcing naturally provides a mechanism for optimistic concurrency control in distributed systems. Each event in the store is typically assigned a version number or a sequence ID. When a command attempts to append a new event, the system checks if the version the command was based on still matches the current version in the store. If another process has appended an event in the meantime, the version check fails, and we can reject the change or trigger a conflict resolution strategy. This eliminates the need for expensive distributed pessimistic locks across multiple database rows. By focusing on the intent and the sequence of changes, we gain a robust way to handle the lost update problem without sacrificing system availability. This takes care of the right side, but how do we query this complex mess of events efficiently for our users? In many applications, the read and write workloads are fundamentally different. A write operation might involve complex domain logic and validation, while a read operation might need to join data from 10 different entities to populate a single dashboard. Traditional CRU architectures struggle because they use the same data model for both, leading to performance bottlenecks and locking issues. Command Query Responsibility Segregation, or CQRS, solves this by splitting the application into two distinct paths. The command side handles state changes and maintains domain integrity, while the query side is dedicated to providing data for the UI in the most efficient format possible. This allows us to scale the read and write infrastructure independently, perhaps using a high-performance RDBMS for writes and a document store for reads. Once separated, how does the query side actually get populated without a direct link to the right DB? The magic of combining CQRS with event sourcing lies in projections. Whenever an event is persisted on the command side, a projector, which is essentially an event handler, listens for that event and updates a specialized read model. These read models are often materialized views designed specifically for a single screen or API response. This means that instead of performing heavy joins at query time, the data is already pre-calculated and denormalized, ready to be served with a simple select per. This shift moves the computational cost from the red phase to the right phase. Since most systems are read-heavy, this is a massive win for scalability and user experience. This looks perfect, but what happens when the read side is a few milliseconds behind the write side? Because the update of the read model happens asynchronously, CQRS systems are eventually consistent by nature. This means a user might submit a form, and for a brief window of a few hundred milliseconds, not see the update on their screen. This can be jarring if not handled correctly at the UI/UX level. We often use techniques like UI-optimistic updates, where the front end simulates the success of an operation immediately, or version tracking, where the client waits for the read model to catch up to a specific version before refreshing. We must accept that in large-scale distributed systems, absolute consistency is often an expensive illusion. Managing this lag requires a shift in how we think about the user journey and system reliability. If it is so complex to manage consistency, why don't we just stick to monoliths and simple databases forever? CQRS and event sourcing are powerful tools, but they introduce significant essential complexity. You should not use them for a simple internal tool with low traffic. That would be over-engineering. However, when you face high concurrency, need a perfect audit trail, or have a domain so complex that traditional CRU becomes a tangled mess of business rules, these patterns are lifesavers. They represent the ultimate decoupling of intent from state. As we move forward, we must realize that these patterns often span multiple microservices, leading us to the challenge of coordinating distributed transactions without a global lock. This brings us to our next critical topic: how to maintain integrity across service bounds when a single event triggers a cascade of actions. Join me in the next chapter as we explore the Saga pattern and how to master distributed workflows. In the monolithic era, maintaining data integrity was as simple as wrapping code in a database transaction block. But in the world of microservices and distributed systems, classic ACDD model atomicity, consistency, isolation, and durability is effectively dead. Attempting to use two-phase commit or XA transactions across network boundaries leads to catastrophic performance degradation and massive lock contention. When service A waits for service B and service B waits for a network response, your entire system's availability drops to the product of every node's uptime. This is where we must transition from the strict ACID model to the base model, basically available soft state and eventual consistency. In high-scale environments like global e-commerce platforms, we trade immediate consistency for system resilience. If you cling to distributed locking, your system will inevitably hang during the first minor network flicker. But how do we maintain any semblance of truth without these locks? We need a mechanism that acknowledges failure as a first-class citizen of the architecture. But wait, if we can't lock the database, how do we prevent a customer from being charged for an item that is actually out of stock? The Saga pattern emerges as the standard solution for managing long-lived transactions without distributed locks. A Saga is a sequence of local transactions where each service performs its work and publishes an event. If one step fails, the Saga must execute a series of compensating transactions to undo the changes made by the preceding steps. Crucially, a compensating transaction is not a simple database rollback. It is a new, separate business action like issuing a refund or sending a cancellation email. This is an application-level recovery mechanism. In the field, we see this implemented as a forward recovery where we keep retrying the next step, or a backward recovery where we undo everything. This architectural shift requires developers to think about business logic in terms of state transitions and failure paths. It sounds straightforward in theory, but implementing undo logic for every single action adds significant complexity to your service design. This raises a critical question: how does this look in a real-world flow like a travel booking system where 3 different companies' APIs are involved? Let's visualize a multi-service travel booking flow: flight, hotel, and payment. First, the flight service reserves a seat. Second, the hotel service books a room. Finally, the payment service attempts to charge the user. If the payment fails, perhaps due to an expired card, the Saga must trigger the compensating transactions. The hotel service receives a cancel room command, and the flight service receives a release seat command. Without a Saga, you would end up with a ghost reservation where a seat is held forever but never paid for, leading to lost revenue. In complex enterprise systems, these flows can involve dozens of steps. The challenge here is data integrity. Because there are no global locks, other transactions might see the reserved state before it is canceled. This is known as the semantic loss of isolation. You must design your business logic to handle these intermediate states, often using pending or provisional statuses in your UI. This process seems logical, but who actually initiates these calls? Does every service need to know about every other service, or should there be a central brain? This is the core debate between choreography and orchestration. The first approach to implementing a Saga is choreography. In this model, there is no central coordinator. Instead, each service works like a dancer following a script. When service A finishes its task, it publishes an event-like order created. Service B, which is listening for that specific event, picks it up, does its work, and publishes payment processed. This is highly decoupled and follows the pure spirit of event-driven architecture. There is no single point of failure in the logic, and it is very easy to add new services by simply having them subscribe to existing events. However, as your system scales to hundreds of services, choreography can become a distributed monolith of spaghetti events. It becomes nearly impossible to visualize the entire workflow or identify where a process is currently stuck without a sophisticated distributed tracing tool like Jaeger or Zipkin. It's a great choice for simple workflows, but is it enough for a complex banking system? Let's contrast this with a more structured approach where a central brain manages everything. The second approach is orchestration. Here, we introduce a central orchestrator or Saga manager, a dedicated component that tells each service what to do and when to do it. Think of it as a conductor in an orchestra. The orchestrator sends a command to service A, waits for a success response, then sends a command to service B. If service B fails, the orchestrator is the one responsible for sending the undo commands to service A. Modern frameworks like Temporal, Camunda, or even AWS step functions provide robust state machine implementations for this exact purpose. Orchestration provides much better visibility. You can query the orchestrator to see exactly what stage a customer's order is in. It also prevents cyclic dependencies because services don't need to know about each other. They only need to know how to respond to the orchestrator. But there is a catch. The orchestrator itself becomes a critical piece of infrastructure that must be highly available and resilient. Is the trade-off of centralized control worth the added infrastructure overhead? Let's compare the two models directly to find the sweet spot for your architecture. When choosing between choreography and orchestration, you must weigh complexity against maintainability. Choreography is excellent for small-scale systems where services are naturally independent, but it falls apart when business requirements change frequently. If you need to add a fraud check step between order and payment, in choreography you have to modify multiple services to change their event subscriptions. In orchestration, you only modify the central state machine definition. From a monitoring perspective, orchestration wins hands down because it provides a single point of truth for the workflow status. However, orchestration introduces a God-object risk where too much business logic drifts into the coordinator, potentially leading to a brittle architecture. Generally, we recommend choreography for simple, high-volume fire-and-forget sequences and orchestration for complex business processes with many failure modes and strict compliance requirements. But regardless of which pattern you choose, there is one technical hurdle that destroys most distributed systems if ignored: idempotency. Why is it the most common cause of double billing and data corruption? Let's look at the implementation checklist. To build a resilient Saga, you must adhere to a strict implementation checklist. First and foremost is idempotency. In a distributed world, at least once delivery is the norm, meaning your service will eventually receive the same event or command twice. If your payment service doesn't check for an idempotency key, like a unique order ID, you will charge the customer twice. Second, you must have a robust retree strategy with exponential backoffs. Network glitches are temporary. If service is down, don't just fail retree. Third, every action must have a corresponding compensation logic that is commutative and idempotent itself. Finally, use dead letter queues, DLQ, for messages that simply cannot be processed after multiple retries. This ensures that a single bad message doesn't clog your entire pipeline. Mastering these sagas is the final technical hurdle for a distributed systems architect. But how do we bring all these concepts, consensus, CQRS, and sagas, into a unified strategy that a real enterprise can actually execute without going bankrupt? In the final chapter, we will bridge the gap from technical primitives to enterprise strategy. As an IT strategy consultant, I often see leaders struggling with the paradox of choice. Choosing between Raft, Paxos, event sourcing, or Sagas isn't just a technical decision. It's a strategic move that dictates your future technical debt. If you require absolute linearizability for financial transactions, the overhead of Raft or Paxos is a necessary tax you must pay. However, if your scale demands global availability, moving towards event sourcing with Saga-based eventual consistency is the only way to survive. This matrix serves as a North Star for architects. We categorize systems based on their tolerance for inconsistency versus their need for throughput. High-stakes enterprise environments often require a hybrid approach where the core state is managed by consensus, while peripheral microservices operate on asynchronous events. Neglecting this framework leads to fragile systems that collapse under the weight of their own complexity. By aligning your business requirements with these technical patterns, you ensure a resilient infrastructure that can scale without losing its integrity. But is today's best choice really enough for tomorrow's emerging challenges? The horizon of distributed systems is expanding, and as we look toward the 2026 ICDCS conference in Seoul, several paradigm shifts are emerging. We are moving beyond the traditional crash fault tolerance models that Paxos and Raft excel in and entering the era of Byzantine fault tolerance, or BFT, even within private enterprise clouds. As AI workloads become distributed by nature, consensus protocols must evolve to handle massive data gradients and non-deterministic outputs. We are also seeing a resurgence in formal verification methods to ensure that our Saga patterns are mathematically sound before a single line of code is written. This timeline illustrates the transition from simple log replication to the complex, multi-layered synchronization needed for the next decade. Understanding these academic trends isn't just for researchers. It's the only way to future-proof your architecture against the next wave of disruptive technologies. If you ignore these shifts, your system will be obsolete before the hardware even arrives. Now, let's tie everything we've learned together into a final vision for your career. We have traversed a rigorous path today, from the mathematical elegance of Paxos to the pragmatic complexity of distributed Sagas. The enterprise strategy isn't about picking one best technology, it's about mastering the art of the trade-off. You now understand that strong consistency is a luxury for critical paths, while eventual consistency is a design discipline for global scale. You have the tools to separate your command and query paths with CQRS, and the foresight to use event sourcing for auditability and resilience. True mastery in system design comes from knowing exactly where your system will fail and building the safeguards to handle that failure gracefully. This deep dive has provided the theoretical foundation, but the true learning happens when you apply these patterns to your unique business constraints. This foundation will be the catalyst for your next high-scale architectural breakthrough in the ever-evolving landscape of 2026 and beyond. This isn't the end of your education, it's the foundation for your next high-scale architectural breakthrough.